Chapter 8, Conservation of Energy by Emily Klein. What is conservation of energy? The conservation of energy is when energy is transferred from one form of energy to another. For example, we'll learn later in the chapter about how energy is transferred from kinetic energy to potential energy and vice versa. When energy is conserved, it is not destroyed, it just changes forms. When we talk about conservation of energy, we refer to conservative and non-conservative forces. What defines a conservative force? A conservative force is when the work done by a force depends on the endpoints. Therefore, the conservative force is path independent, depending only on xf and xi. One example of a conservative force is the spring force, where the end force, the work done by the spring force, depends only on the xf and the xi, the final and initial positions. As you can see, the work done by spring is the force done by spring times the delta x, or the integral of negative kx dx. Therefore, we can see in the final equation, once integrated, that this work done by spring depends on the xf squared and the xi squared, only the endpoints, and therefore is path independent. Another common example of a conservative force is the force of gravity. The work done by gravity is the force of gravity times the delta y, or the y position final minus the y position initial. As you can see here, the work done by gravity depends only on the y final and y initial positions, and is therefore path independent and a conservative force. Now that we know what a conservative force is, the next question asked may be, what is a non-conservative force? A non-conservative force is when the work done depends on the path taken, not just the final and initial positions. In a non-conservative force, energy is taken out of the system, not transferred to another form, such as kinetic or potential energy. In this case, the energy lost cannot be obtained again. The most common non-conservative force is friction. The work of friction can be seen as equaling the force of friction times the delta x. The longer the force of friction is active, is the more net work done. For example, the longer you push a box against a rough surface, the more net work is being done because the path that the box takes is longer. This being said, we can see that the force of friction depends on the path taken and is therefore a non-conservative force. Next, we know that the net work done equals the total work done, and now that we know the difference between conservative and non-conservative forces, we know that the total work done equals the work of the non-conservative forces plus the work of conservative forces. However, we also know that the net work of a system equals the change in kinetic energy of the system. Therefore, we can conclude that the change in kinetic energy of the system, or 1/2 mvf squared minus 1/2 mvi squared, equals the work non-conservative plus the work conservative of the system. Looking back, we know that kinetic energy is the energy of motion. The formula for kinetic energy equals 1/2 mv squared. However, earlier in the video, I mentioned potential energy. What is potential energy? Potential energy is the energy that could be converted into kinetic energy. For example, a ball at the top of the cliff has potential energy because it has the potential to roll off the cliff and be moving in a downward motion as it falls from the top of the cliff to the ground. It has the potential to be converted into the energy of motion, or kinetic energy. When talking about potential energy, it's important to remember three things. Potential energy is only specified for path-independent or conservative forces, where the energy within a system is conserved and not taken out of the system, like it is for non-conservative forces like friction. Potential energy is also different for different conservative forces. Example, the potential energy for a spring force would be different than the potential energy for the force of gravity. Finally, it's important to remember that the potential energy is associated with a change in position, often from a height. For example, the ball at the top of the cliff going to the ground would be a change in position in the y direction. In physics, the change in potential energy is represented by delta U, or the opposite of the work done by conservative forces, equaling the negative work done by conservative forces. For example, the change in potential energy, delta U, equals the opposite of the work of the conservative force, gravity. Delta U equals negative mg yf minus y1. The work done by gravity is negative because G equals negative 9.8. Therefore, when the equation is completed, the change in potential energy delta U equals mgyf minus mgyi, or mgy final minus mgy initial. The formal definition for potential energy gravitational is mgh, or mgy, the force of gravity times the height, or y value of the function. Potential energy is the potential amount of energy that is being stored and could be used by a conservative force within a conservative energy system. As can be seen, the amount of potential energy represents the amount of energy that has the ability to be transferred into kinetic energy that can be transferred into thermal energy in the system. As we just saw, potential energy equals the opposite work done by conservative forces, or the negative work conservative. Here is an example of this, showing the potential energy of the spring equaling 1/2 kx squared. Looking at the graph, we can see that when the potential energy is at the minimum, the kinetic energy, or the conservative force, is at its max, and vice versa. When the kinetic energy equals 0, the potential energy is at its maximum value. Shown in this graph is another example, showing the conservative force of gravity equals mgy. The potential energy of the conservative force gravity equals mgy. When the potential energy graph is at its highest point, the kinetic energy graph, shown by the dotted line, is at its lowest point. A final way of illustrating this point will be by looking at when the kinetic energy increases, the potential energy decreases. Shown again, as the potential energy increases, the kinetic energy decreases. When one is at its maximum, the other is always at its minimum. Looking at this diagram, we know that only conservative forces are present in the picture, seeing as there's no air resistance or friction present. Knowing this, we can see that the change in potential energy equals negative work done by conservative forces equals mgh, or the potential energy function for the force of gravity. We also know that the total forces equals work conservative, because there's no non-conservative forces like friction or air resistance in the picture. This being said, we know that the work done by conservative forces equals the change in kinetic energy, and therefore the work done by conservative forces equals mgh. Knowing this, we can see that the work done by a conservative force is equal to the negative of the change in the potential energy function, shown once again as work done by conservative forces equals mgh, which is positive because g equals negative 9.8 meters per second squared. We know that net work equals the change in kinetic energy. We also know that the change in kinetic energy equals the work conservative plus the work non-conservative, which equals work net. Next, we learn that work conservative equals the negative of the change of potential energy, so work conservative equals negative PE. Plugging this into our original equation, WC plus WNC equals delta KE, we see that the negative change in potential energy plus work non-conservative equals delta KE. Therefore, work non-conservative, such as friction, equals delta KE plus delta PE. But this also equals mechanical energy total. Work non-conservative equals mechanical energy total. We also must remember to factor in potential energy gravitational and potential energy spring. Therefore, work non-conservative equals delta KE plus delta PE spring plus delta PE gravitational.